Welcome to iLecture Online, and here's another example of how to do a problem dealing with momentum. Again, two things are colliding, and as we know about momentum, whenever two things collide, momentum is always conserved, which means that the momentum of the two objects before the collision always equal the sum of the momentum of the two objects after the collision. Now, in this particular case, we have an elastic collision, which means that also the energy is conserved. In most real collisions, energy is never conserved. That's called an inelastic collision. But here's an example of an elastic collision where the energy is conserved as well. An elastic collision also implies that the two objects will not stick together after the collision. They will go their independent ways after the collision. And so typically we'll have to find both of the velocities of the two objects after the collision. So if you want to solve a problem like this, and here's the example, we have a 1 kilogram bowling ball which is moving to the right at 2 meters per second, and it collides with a stationary 3 kilogram bowling ball. What will be the final velocity of both balls after the collision? And assume an elastic collision, like I told you already. All right, so let's draw a little picture here. We have a smaller bowling ball colliding with a bigger bowling ball, which is stationary. So this is mass 1, this is mass 2. Mass 2 is bigger, so this is equal to 1 kilogram. This is equal to 3 kilograms. The velocity initially of the first one, so V1 initial, is equal to 2 meters per second to the right. And the velocity of this one, V2 initial, is equal to 0. So I'm using the subscripts 1 to indicate the small bowling ball and 2 to indicate the bigger bowling ball. Now they will collide, and I'm assuming that the small bowling ball will collide with the big bowling ball and be pushed backwards, and the big bowling ball will be pushed to the right. But again, not 100% sure that will happen. We're not sure what will happen to the two balls. The equations will let us know what happens by solving the problem. So starting out, we say momentum initial equals momentum final. That's always the case. And the momentum initial will be m1 v1 initial plus 0. So the momentum of the first ball is mass times velocity, but the momentum of the second ball is 0 because there's 0 velocity. And so that equals m1 v1 final, which is what we're looking for, plus m2 v2 final, which is what we're also looking for. So we need both velocities. Now, we have one equation and two unknowns. So you can't solve two unknowns with just one equation, which means we need a second equation. We also know that energy is going to be conserved, and that provides us our second equation. So we can say that E initial equals E final. And the only energy we're dealing with here is kinetic energy, not potential energy, because the height is not changing. So we can say that the kinetic energy of the first ball plus the kinetic energy of the second ball initially, that must equal the kinetic energy final of the first ball plus kinetic energy final of the second ball. All right, and kinetic energy, as you know, is 1/2 mv squared, so 1/2 mass 1 v1 initial squared plus 0, because since the second ball is not moving before the collision, it has no kinetic energy. So that would be equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So the kinetic energy of the first ball must equal the sum of the kinetic energies of the two balls after the collision. So now we have to solve these two equations simultaneously. Well, first of all, looking at this equation, I can see that we can divide, or at least multiply both sides of the equation by 2 to get rid of the 1/2. And then let's plug in the values for the masses and for the velocities that we know. So since the mass is 1 for the first ball and 3 for the second ball, and the velocity is 2 for the first ball, let's plug those values in. So we have 1 times 2, and I'm going to leave off the units. That makes the equation a whole lot cleaner to work with, is equal to 1 times v1 final plus 3 times v2 final. And so putting everything together, we can say that's 2 equals v1 final plus 3 v2 final. All right, there we go. We're going to do the same to the second equation, the energy equation. So we can say here that 1 times 2 squared equals 1 times v1 final squared plus 3 times v2 final squared. All right. What do we do next? Well, we have now two equations and two unknowns. We have V1 final, V2 final here. We have V1 final, V2 final there. So we have to somehow solve one equation for V1 final or V2 final, whichever you prefer. It's probably easier to solve this for V1 final and plug that into the second equation, eliminating one of our variables. So let's solve this equation for V1 final. So V1 final is equal to 2 minus 3 V2 final. By moving the 3 V2 final to the other side, it becomes negative. And then we'll take this and plug that into our equation over here. And replace V1 final by what V1 final is equal to in terms of V2 final. Of course, on the left side, we get 1 times 2 squared, which is 4. So we get 4 is equal to V1 final squared times 1. This is V1 final, so we can write 2 minus 3 V2 final, quantity squared, plus 3 V2 final squared. All right, now we can see that we now have a single equation with just one variable, and let's solve that variable for V2 final. We first have to multiply this out, so we get 4 equals 4, 2 times that's minus 6, that's minus 12 V2 final, plus 9 V2 final squared. Again, when you multiply or when you square a binomial, you take the first term squared, you take the last term squared, and then twice the product of the two terms. 2 times the minus 3 V2 final is minus 6 V2 final times 2 is minus 12, and then we still have the plus 3 V2 final squared over here. Then nicely we can eliminate a 4 on both sides of the equation, and then finally when we combine like terms, we have 0 equals minus 12 V2 final, and 9 plus 3 is plus 12 V2 final squared. All right, now we can see that we have a quadratic equation, but a relatively easy one because we don't have the third term, we don't have the constant term, so we can actually divide both sides by 12. So we'll do that, so we get 0 equals minus V2 final plus V2 final squared, and then we can factor out of V2 final, so we say 0 is equal to V2 final times minus 1 plus V2 final, like so, and that is then set equal to 0. Now whenever we have something set equal to 0, like in this case a product, we have V2 final multiplied by 1 minus V2 final. Whenever we have two things that are multiplied together and the result is 0, that can only happen if either one or the other equals 0. So from here we can then say that means that V2 final equals 0, or minus 1 plus V2 final is equal to 0. And of course that's true when we move the 1 across, we can say that V2 final equals 1. So one of these two equations or one of these two solutions must be the correct solution. So either velocity 2, the velocity of the big ball after the collision is 0, or it is equal to 1. Now, you need to kind of think about that for a moment. Do you think it's possible that we have this ball hitting this ball and this ball doesn't move at all? That no energy is imparted on it and it doesn't get pushed. And then this ball will simply then get pushed back in the opposite direction. That doesn't seem plausible, right? Because if the momentum before the collision is to the right, and this ball doesn't move after the collision, there's no way that this ball can then be pushed back to the left. Obviously, it cannot surpass this ball because this ball would then be in the way. So logic dictates that it's not possible for the velocity of this ball after the collision to be equal to 0. So we say that's not physically possible. So the only option then is that V2 final equals 1. So if V2 final equals 1, we can then go back over here, take the solution here, and plug it back into that equation, and then find out what V1 final is equal to. So we can then say that V1 final is equal to 2 minus 3 times V2 final, which was 1 meter per second. So that's 2 minus 3, which becomes now minus 1. Of course, the answer is meters per second. So our solution then is that after the collision, V1 final is equal to minus 1 meter per second, and V2 final is equal to a plus 1 meter per second. So V1 final equals minus 1 meters per second, and V2 final equals plus 1 meter per second. And that is the solution to this problem. So again, recapping, we had a problem where two balls are colliding. Now, this ball is stationary before the collision. This ball was moving to the right at 2 meters per second. The two balls collide. You're not quite sure what happens, but you do know that it's an elastic collision, which means that they have independent velocities after the collision. The assumption is that the big ball probably moves to the right, the little ball probably gets pushed back, but you don't know. They may both be moving to the right after the collision. Let's find out what the solution is. So you start out by saying that the momentum is conserved. Of course, therefore, the sum of the momentum before the collision equals the sum of the momentum after the collision. But since it's elastic, you can also say that the energies are conserved. So the sum of the energies before the collision equals the sum of the energies after the collision, which is a good thing because notice that by using the equation of momentum, we end up with two unknowns, V1 final and V2 final, which cannot be solved with just a single equation. But using the second equation, the conservation of energy, we get a second equation with the variables V1 right here and V2. And so what we do then is we solve one of the two equations. Typically, you like to use this one because it's easier. You solve the conservation of momentum equation for one of the two variables. You then plug that into the other equation to eliminate one of the two variables. When you do that, you end up with a quadratic equation. You solve for the quadratic equation. You then realize that one of the two solutions could not possibly be the correct one. And so you find the right velocity final for the one object, and then you use this equation to find the second velocity final, realizing, of course, that the units were in meters per second. And that's how you do a problem like that.